In this video, we're going to talk about a important vocabulary. Let me try to let me start that over. In this video, we're going to do an important vocabulary review for Calculus 1. These are certain theorems and definitions that will make doing calculus handy and more convenient for you as you have them memorized and have an intuitive understanding of how they work. Right away, we'll talk about the first derivative and second derivative and how they relate to certain physical concepts. Me coming from as a physics student, I always try and impress on these important relationships between the derivatives and their physical meanings. So the first derivative represents the slope of the tangent line, is the common first definition or phrase that you learn. The way I like to think about it is that this is the instantaneous rate of change at a particular point in time. The point in time would be dictated by like this, where x is equal to a type deal. And this type of derivative actually gives you the velocity of the point, the velocity of the graph at that point. Because if we think about it, this slope of the tangent line or instantaneous rate of change now gives us an equation for the rate of change across the graph as you move. So the rate of change over a distance is the same thing as a velocity. Similarly, if we take the second derivative or the derivative of the first derivative, you have the slope of the tangent line or the instantaneous rate of change of the instantaneous rate of change. If you have the rate of change of the rate of change, this is synonymous with calling it an acceleration. So basically what I really want for you to understand is that the first derivative with respect to x is synonymous with velocity. And then the second derivative is equal to acceleration, or the derivative of velocity. So in calculus, when we're learning about, we really learn about derivatives just so that we can learn about integration. Integration is like the most valuable math technique there is, in my opinion. They're like most of the hugely important like physical concepts that we get out of math come from doing integrals, because there's just so many things that they represent, meaning that like they represent like the area under the curve. They represent an infinite summation, because when you're doing an integral, that's like the same thing as this thing right here. An integral is like the same thing as doing like a summation when you're doing a summation from 0 to whatever, 0 to infinity, if this is undefined type deal. Because it represents a summation, then that also means that you could find like volumes and arc lengths and then center of mass and all of that good stuff can be represented and found using integration. So integrals are a very important concept. So recall how to take an integral and what it really is. An integral is just the act of doing anti-differentiation. And anti-differentiation just means like if you know how to take a derivative, then it's the same process but going backwards. That's why in calculus they typically teach you about how to take a derivative first, because once you learn all of the rules and steps and nuances like power rule, product rule, and like chain rule and all that stuff, then taking an integral is essentially just like employing a reverse of all of those methods which makes it a little easier if you already know what they are before teaching it to them. So that's that. Next, we have some important theorems to discuss and review. The most important, or the bread and butter of all of these reviews, or all of these theorems, sorry, is the Rolle's theorem, or the mean, or which leads to the mean value theorem. So the Rolle's theorem is the one where it goes, if you have a function or a graph that is continuous between some interval a, b, and is differentiable, meaning that like there is no breaks or sharp points. So some graph that's smooth and connecting, and some place that has, I didn't do that well, hold on. If it's smooth and connecting and differentiable on the open interval a, b, and their endpoints f of a equals f of b, that basically just means that at their endpoints, they have the same y value, which I tried to roughly do here. If they have the same y value, then this theorem means that there exists within this interval a critical point. A critical point is somewhere along this graph, this value c, which is in between the interval, there exists a derivative where this is equal to 0, or where the slope is horizontal. So that means that like a critical point is some place where the slope goes from being some sort of either positive or negative to being either negative or positive. So this one is negative and goes to positive. Therefore, somewhere in the middle of this graph, which we can obviously tell is right here, there's a slope that's horizontal or equal to 0. Because the slope is negative, 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 getting less negative, and then eventually the slope is 0, and then it gets positive, 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 positive. So whenever the slope is 0, or you have a horizontal tangent line, that's where we have a critical value right here. The mean value theorem is more of just like an extension of like this type of process. So suppose that like all of those earlier conditions were satisfied, and now we're trying to say that there exists a derivative within this function that exists pretty much, because right here is essentially the framework for the definition of a derivative. So basically that's all the MVT is that suppose that if you have the same type of conditions where if it's continuous on the closed interval and differentiable on the open interval, then there exists some derivative that exists. Also a quick, so most of the time when you have something that's continuous, it's also differentiable, but that doesn't happen 100% of the time. So there is a reason why they included to specify continuous and differentiable, because for instance, if you had a graph that was continuous on this interval a, b, but looked like this, with some really sharp turns, there's technically a rule or a problem here where it's because it has this very sharp turn, there's not really a point that has a slope that's 0, meaning that it's undifferentiable right there. So you can have a continuous graph where there's no breaks and no jumps, but it still breaks the rule because these are not differentiable points on the graph. Then the last theorem is the intermediate value theorem that we'll review. This one's also very kind of intuitive once you're starting to get the handle of how these conditions are met. It goes for any function f that's continuous over the interval ab. The function will take any value between f of a and f of b over that interval. This also means for any value L between f of a and f of b, there exists a value C within a and b such that f of C equals L. So this, as I was trying to say, is kind of something that is intuitive or would intuitively make sense for any graph between 2 points that is continuous. If you have a function that's continuous over the closed interval, then the function will take any value between the two y values over the interval.